Hello everyone, and welcome to the Compass seminar today. Today our speaker is Dr. Bryant Xing, who is a postdoctoral student with Dr. Ellipot's group. He completed his undergraduate degree in physical oceanography at the Ocean University of China and the University of Tasmania in Australia. He received his doctorate in physical oceanography at the University of Tasmania, and he recently joined Rosenstiel in September. He is continuing to pursue ocean circulation dynamics, ocean modeling, and data analysis. When he isn't studying our oceans, Bryant enjoys playing basketball, hiking, and cooking. So thank you everyone for coming today, and please enjoy the presentation.
Thank you for the introduction. Hello everyone, I'm Bryant. As I introduced, I'm new postdoc to Rosenstiel and will focus on the AMOC meridian coherence. But today I'm going to give a talk about some results of my PhD program, how the complexity of the Continental breakup controls early ACC. And firstly, I'd like to give some research background of my PhD program. During Eocene-Oligocene transition, around 34 million years ago, the globe underwent a decline of atmospheric CO2 concentration and a sharp rise. Probably you can see from these two figures, a sharp rise in Antarctic glacial volume. This marks a climatic transition from greenhouse to icehouse. And also during the EO transition, the Southern Ocean circulation also changed dramatically. So we know that the modern Southern Ocean connects all global oceans without any meridional continental barriers. And there are subtropic and subpolar gyres in the modern Southern Ocean. And there are also two Southern Ocean gateways, Tasmania Gateway here and the Drift Passage here, to allow the Antarctic Circumpolar Current to be the strongest current in the world. However, in contrast to modern pattern, the Eocene or early Southern Ocean was relatively warm, and ice accumulation was spread during EO transition. A big difference between early and modern Southern Ocean is the prevalence of the ACC. During EO transition, the circumpolar current in early Southern Ocean is a TJ through flow. Here, a TJ through flow from Australia and Antarctic basin, and its extension in the Pacific. It cannot be turned as a ACC, but can only turn as a proto-ACC. But this raises a question of how and what drives the evolution of the proto-ACC. There are two common drivers: it's the gateway opening and deepening, and the wind stress modification. I won't go details the dating of ocean gateway opening and deepening, but I will introduce their role in changing the proto-ACC during EO transition. A recent study applied quarter degree eddy permitting ocean model and realistic paleobathymetry to simulate that the subpolar gyres indicated by the green colors dominate the high latitude when the TJ is at 300 meters. When TJ deepening from 300 meters to 1500 meters, the subpolar gyres gradually weakened and shrunk. And when accordingly, a stepwise cooling of the Southern Ocean. Here, probably you can from the right columns. And when TJ is at 1500 meters, the subpolar gyres is weakened to around 10 small drops, and there forms a strong and not really strong. It's a proto-ACC indicated by red arrows. such proto-ACC has a strength of 29 spore drops, only about 15 to 18% of the modern ACC. And so that means the only gateway deepening is not enough to allow for a modern ACC transport. So we probably can consider another key factor, wind stress. There are two papers talking about the effect of wind stress. Sure, 2015 used geological evidence to show that around 13 years ago, with the migration of the TJ into westerly wind band, allows an eastward geostrophic current. And Monday 2015 used idealized ocean model to show that the including or excluding of continental barriers, this one, and bathymetry ridge, the shedding, can largely affect the sensitivity of circumpolar transport to changing wind stress. However, uncertainties remains in these two studies. The hypothesis proposed by Scher's work was not tested in the ocean model, and the Monday's work used a highly idealized bathymetry and the ocean model to test the effect of wind stress. While all of this study inspired of the first part of my PhD program, how longitudinal position and strength of wind stress controls the evolution of the proto-ACC. For method, we applied quarter-degree eddy permitting ocean model based on MIT GCM, and we also applied realistic paleobathymetry reconstructed to 38 minutes ago. We set two TJ depths. One is 300 meter and one is 1500 meter. And we remind the DP depth as 1000 meter. And we apply 4 normal wind stresses with only difference in longitudinal position. And we apply another doubled wind stress to the 15 south and the 16 south. So here now we have 12 model simulations listed here. For results, with the 300 meter TG, we reproduce the late Eocene Southern Ocean circulation patterns, but are consistent with the previous work. And with the 1500 meter TG, the right columns planes, the southward wind stress migration can lead the further shrinking of the subpolar gyres. And when the wind migrating to 16 south, this case, we got a strong and coherent circumpolar current in this case, and the DP transport is 38.3 small drops, but still only around 1/3 of a modern ACC transport. Then we would like to see the response of a gateway transport to double the wind stress. From this figure, the TJ transport indicated by red columns is largely strengthened in all simulations. So the maximum TJ transport is increased by doubled wind stress to 75.4 small drops. And DP through flow transport, indicated by blue columns, they are negative westward when TJ is at 300 meter, and positive eastward when TJ is at 1500 meter. They are slightly increased in most simulations, with the increase lower than 35%. And also with the 1500 max 16 south case, the doubled wind stress increased the circumpolar transport to 44.8 small drops. So from from above results, we can see in 1500 max 16.3 case, we got a strongest and coherent proto-ACC. But why it happened? Probably we can compare with the latitudes of wind stress and ocean gateways. We can see the latitudinal position of a maximum westerlies of 16.3 south exactly located at the northern margin of the DP. Such alignment can allow the eastward current penetrate the DP, almost penetrate the DP, and close the circumpolar path rather than flowing poleward. So we mean that when TJ is deep, like 1500 meters, the alignment both Southern Ocean Gateway, TJ and DP, and the maximum westerlies allows the maximum transport of a proto-ACC or onset of a proto-ACC. Another question you might have, why insensitivity of a DP transport? Before answer this question, I would like to introduce a theory in physical oceanography, the eddy saturation. This means this refers to insensitivity of ACC volume transport to changing wind stress if we use eddy-rich models. In details, the increased wind stress can generate more energetic eddy field, and such eddy can transmit the momentum input from wind stress vertically. And so the momentum input from wind stress is balanced by pressure differences across the bottom bathymetry. Here we refer to bottom foam stress. Such process can take place without steepening the mean isopinnate, so the mean transport does not increase even with increased wind stress. And in this study, the complicated submerged bathymetry in DP region allows the DP through flow to generate a deep bottom foam stress. So from this figure, we can see the dark blue curve showing the deep bottom foam stress. Such deep bottom foam stress can respond strongly to change in wind stress. From the two panels, you probably can see the dark blue curves can respond to the doubled wind stress. So this due to the eddy vertical transmission. So this deep foam stress, bottom foam stress, is expected to balance the doubled wind stress and break the connection between mean flow and the wind stress. So probably can allow the strong eddy saturation of the DP transport. And more details about eddy saturation and zonal momentum balance, I refer to the two papers and my paper. So to sum up, if we only have a wind stress migration, we can get a DP transport around 38.3 spot drops. If we including the wind stress strengthening, like double the wind stress, the DP transport is increased to 44.8 spot drop, while the modern ACC DP transport is around 137 spot drops. This means the wind forcing modification with a gateway deepening still cannot get a modern type ACC. This raises another question: what drives the increase of DP transport to modern value? Then, in physical oceanography community, surface buoyancy forcing associated with fluxes, heat, and salt at the surface at the ocean surface is widely recognized as a driver of the deep water formation and overturning circulation. While there are two papers used the ocean model to show that the buoyancy forcing probably can control the ACC transport. And a recent study also used the eddy reserving ocean model to show that the deep water formation around Antarctica due to buoyancy forcing, due to buoyancy north, can regulate the circumpolar current transport. So based on these studies, we are motivated to investigate whether the surface buoyancy forcing makes an active contribution to the evolution of the proto-ACC. For method, the model domain and wind stress and the paleo surface buoyancy forcing are the same with the last studies, but this study derives another three kind of new surface buoyancy forces from extracting sea surface temperature and sea surface salinity from mimic. And there are three steps adjustment to the initial data to match our model domain. And then we still have two TJ depths, 300 meter and 1500 meter, and now we have four kind of surface buoyancy forces. And then we conduct 6 model simulations in this study. For results, these 3 experiments using paleo temperature forcing, from this figure, probably you can see these 3 experiments, the A, C, D. They show a ball shape of isosmoles and isoheliums in the upper ocean, and associated with a strong near-surface stratification. And then the westward, the blue, and eastward red jets in the upper ocean indicates the boundaries of subpolar and subtropic gyres. And the velocity, the zonal velocity here in the latitude of 15 south to 16 south indicates a weak proto-ACC and confined to the shallow depths. However, another 3 experiments using modern temperature forcing, the B, E, F, we probably can see extremely deep isosmoles and isoheliums in the Southern Ocean, and they are even extended to the ocean floor in the south of 16 south, indicating a full depth wake stratification. Such wake stratification can induce a deep mixed layer and associate with a vigorous full depth deep convection in these regions. And the zonal velocities in these 3 experiments becomes much stronger and also reach the bottom. From the upper figure, we can see again these 3 experiments using paleo temperature forcing share a similar distribution of a no-eddy kinetic energy field. And the ocean gyres indicated by contours have a strength of around 15 kilograms. And from the lower figure, we can see the maximum mixed layer depths are around 200 and 300 meters and concentrated on the proto-ACC region. In contrast, another 3 experiments using modern temperature forcing show the maximum mixed layer depths almost across the Southern Ocean has reached the ocean floor around 5,000 meters. Such deep mixed layer implies implies a vigorous deep convection occurring in these regions. And also from the up figure, we especially the two experiments D and F. These two experiments use deep TG 1500 TG and modern temperature forcing. There are strong eddy kinetic energy field showing by the red color, the dark red color, and overlapping the deep convection regions. And the ocean gyres in these two experiments have a strength of 300 spectrograms. Then we estimated the transport of a proto-ACC. From this figure, we can focus on this experiment, 1500 modern SPF. This experiment uses deep TG and modern temperature and salinity forcing. This experiment has the strongest TG and DP transport comparable to observation and model estimates of a modern ACC. So based on all of this study, I can probably propose some case for the development of the proto-ACC. Firstly, TG deepening is a vital prerequisite for the onset of a proto-ACC. And then deep convection caused by destabilizing surface buoyancy forcing lead to a more baroclinically unstable ocean. And this allows for the potential energy supplied by surface buoyancy forcing to be converted to the kinetic energy. So the proto-ACC can be largely strengthened. Finally, I would like to give a recipe for the evolution of the ACC. During Eocene and Eo transition, before 34 million years ago, around 15 to 34 million years ago, the rapid deepening of the TG and DP can allow the inception of a gateway through flow, like a TG through flow or DP through flow, that connect all of the main basins, like Pacific and Atlantic basins. And then the latitudinal alignment between gateways and the wind stress maximum lead to the onset of a weak proto-ACC. This leads to a basin scale interruption of the polar heat transport from the tropic to high latitudes. And the weakening the polar heat transport and declining atmospheric CO2 may be related to Antarctic glacial expansion and ice sheet expansion during different periods. And the Antarctic glacial and ice sheet expansion would destabilize the surface buoyancy forcing at high latitudes, leading to a deep water formation near Antarctica and increasingly strengthens the weak proto-ACC and further blocks the polar heat transport. So all of the processes eventually form a positive feedback, leading to a rapid cooling of the Southern Ocean and the formation of a modern ACC. Okay, that's it. Thank you.
Thank you so much. That was a great talk. Does anybody have any questions?
Yep.
Yes, very interesting talk. So basically you say without the thermohaline composite component, the ACC would never go over 40 Sverdrups transport. Is
Sorry?
that correct? Did I understand it correctly? That you need the buoyancy differences to make the difference in the ACC to the Northern Ocean from the Eocene?
Okay. So, pardon?
So you say that the increase of the salinity in the surface water and the mixing actually leads you to the strengthening of the Antarctic
Okay, yeah. So I got your question. So you probably can see this experiment. We use this one. The 1500 paleo T and modern S is we use the modern salinity forcing. The transport is not really increased. So I do think this is probably due to the non-linear ratings of the equation of the seawater, equation of a state of seawater. So such non-linear ratings can cause a situation while in warm water or in warm ocean, like a Eocene-Southern Ocean or tropic ocean, the temperature forcing might have a dominant role in setting density, and the salinity will have a minor role. I'm not sure.
Yes. So, but when did this transition occur? When did you do that from the Eocene to when did it happen? Because the sedimentary record shows that actually the ACC of the whole global circulation really increased around 13 million years ago. Within about 500,000 years, all the currents, the Gulf Stream started to increase very much, in the Indian Ocean, the East Pacific currents strengthened to 3-4 times from what they were before. So basically what you show is the ACC. In the Eocene, yes, it probably was 30 to 40 square-troops to transport, and now today it's 300. But when exactly did that happen? From the sedimentary record, it would show that this all happened around 13 million years ago.
Yeah, definitely.
So we saw all of a sudden an increase in salinity in the world's ocean.
Yeah. Exactly, and this is a really long time, and I'm not really sure the salinity will change a lot from Eocene to now. I'm not really sure, but exactly happens is the temperature changed a lot from the early to modern Southern Ocean, and I haven't investigated the change in salinity. I haven't investigated the change in salinity, so it's quite a combination between wind stress and gateway deepening or widening, and also change in temperature and salinity or probably density. This is a quite complicated role. So I really want to find probably the dominating role of a surface buoyancy forcing, especially temperature. But as I have mentioned, in Eocene-Oligocene is a warm ocean, so temperature maybe have a primary role. But when the ocean is cooled down, maybe salinity can have a primary role again. So I'm not really sure.
Well, you said that you said that the heat transport to the polar regions decreased. But isn't it when the Isthmus of Panama came up and when the Tethys closed between Africa and the Asia, actually that's when the Circumpolar Current shut down and we had more heat transport to the north. And the first most Atlantic depot
yes.
From the thermal circulation, the first indication of southward flow of that current was around 18 million, and then it increased rapidly around 12.5 million years. So isn't other gateway closure and opening part of that whole picture, and especially for the evolution of the salinity in the world's ocean?
Yeah, exactly. During the similar time, I'm not really sure the name of there is a gateway between American, sorry, I forgot the name, and also the Arctic have another gateway.
Yes.
And they do have some the role in setting the salinity and the temperature. And for my study, I only focus on Southern Ocean, so I do not have really results about the North Hemisphere. But in my paper, I do show the results. It's a heat transport. In my sensitivity experiments, the heat transport is decreased, and probably the heat transport can be transported to another basin due to the onset of a proto-ACC. Sorry, not really sure.
So, but what is your estimate of how you increase salinity to the modern ACC? How do you do that?
How to estimate the salinity in modern
Or
ACC?
what controls it? Why did the salinity in the world's ocean change to make that the buoyancy difference that we have today?
That could
Do
be.
you know the answer? Or?
No.
We don't know the answer. Okay.
So, well, we know that, for example, with the rise of distance of Panama, we start to have evaporation in the Caribbean basin, then Yucatan basin, Gulf, so that's why we increase the salinity in the Gulf Stream. Likewise, in the Indian Ocean, when we start to close the Africa up to the Asian plate, we have an increased salinity in the Indian Ocean. So there are gateways that close and increase ocean basin salinity. Is that enough to increase the buoyancy difference in the whole world?
So that's a question we don't know.
Yeah.
Thank you.
I have another question for you. So you run a lot of runs, simulations, right? But I was just wondering, did you actually use your model to do like modern bathymetry, modern buoyancy forcing?
No.
And to try, or is it already done? Is that from Maslow et al, or is that?
Yes, this is modern observation and also the modern estimate by these papers. So.
Yeah. So Maslow must be like the ocean state estimate, right? But I'm just wondering if your model, in its configuration, was able to reproduce like the modern ACC at all. If you had the modern bathymetry and modern buoyancy forcing, do you get the right ACC in your model?
I'm sorry, I haven't run such modern bathymetry and modern buoyancy force, surface buoyancy force now, but. Because my model is half. It's just a focus on southern hemisphere, and I also do not couple the atmospheric component, and also we use the paleo wind stress. So I cannot get a modern estimate with my model. But yeah, I do think if I couple the atmospheric and the sea ice simulator, probably I can do that. But it definitely costs a lot, I think.
Yeah. Just as a null hypothesis, right? Yeah. Just to see if your model was able to replicate the modern ACC, and then you can modify it and use like the proto-ACC. Just a question.
Yeah, for sure. Thank you.
I have a question on the eddy saturation theory.
Okay.
You use it to explain the result from your model, right?
Yep.
But your model is actually eddy permitting.
Yes, definitely.
I just wonder, so your eddies are parameterized?
Yeah.
So.
Not really parameterized. It's It's not eddy reserving or eddy reach, it's eddy permitting, but definitely can a little bit describe the eddy activities. So it's not really precise with as many as the really high resolution model, but it definitely can work, I think.
So you use half degree.
It's a quarter degree. It's quarter degree.
What degree?
Yeah.
Okay.
So, and that probably can, if we use an eddy reach, we can get a full eddy saturation of the transport, of the circumpolar transport. But now you can see the DP transport is increased a little bit due to the increased wind stress. So then that's pretty much due to our not really high resolution model.
Okay, so you're seeing the eddy saturation still occur in your model.
Yes.
Okay, so the parameter, the partly parameterized eddies can give you the theory, right? Can give you the balance.
Mm-hmm.
Wind stress and pressure. Even though the eddies are partially parameterized.
I don't think our model uses parameterization, so I'm not really sure the eddy parameter can give a part of works. I'm not really sure, but
But I think this is what it's showing in that figure, right? So it's showing like the balance between the form stress and the momentum input, right? Is that what it is? That figure is showing you that mechanism that you invoke, right? Seems to be the case in the model.
Exactly.
What is the light green?
the light blue is shallow because I separate different depths. Yes, the dark blue curve shows. Sorry, I'm not really sure you can see.
No, I cannot see. What is it?
It's a 380 meters.
Okay.
It's larger than, deeper than 380 meters. And the shallow one is lower than 380 meters. And we can see the actually in circumpolar belt around 40 to 60 south, the shallow bottom pump stress is not sensitive to the double wind stress. Then that might can explain why there is a sensitivity of a TG transport.
But is that zonally average or is that just in drag passage?
As on average.
Not here, right?
Any questions in the Zoom audience? All right, thank you.
Just not quite sure. Do you want to have the proto-ACC the same strength as the modern one? Do you think it should have been the same in the EOC than it is today?
So I run idealized experiment. So I want to say the early proto-ACC has the similar strengths to modern ACC. It can be impossible. It can be impossible because the gateway is still shallow and narrow, so it probably cannot give so much volume. And also, but what I do is just pick up the primary driver of increase the proto-ACC transport.
From the geological record, I would say it should not be as strong as this today.
Yeah,
It should
definitely.
be
Probably can see.
I liked it when he said it's like 30 to 40 spectrums, and then at the time, I would say perfect. That's what it should be.
Yeah, exactly. You can see the deep the deep condition or the deep mixed layer is
It's much more modern than
yeah, exactly. It seems like ridiculous, but it's just idealized experiments.
Very nice. Thank you.
No worries.
Thank you.